Chapter 6.1, Area of a Region Between Two Curves. Yesterday we saw how the area of region between two curves was simply a matter of taking the definite integral of the top function minus the integral of the bottom function. We're going to look at that some more today. We're also going to look at when we do it sideways. So maybe we're not always in terms of x. Sometimes we're going to be in terms of y. Let's look at an example. Here we have two graphs that intersect. They intersect at more than one point in this case. So find the area of the region between the graphs of y equals 3x cubed minus x squared minus 10x and y equals negative x squared plus 2x. All right? So we're going to start by graphing this. All right? So we'll graph y equals 3x cubed minus x squared minus 10x, and we're going to graph negative x squared plus 2x. Right? Zoom to a standard window. That's the window that best shows this. Right? I graph that right. 3x cubed minus x squared minus 10x. Right? So this is the window that shows it best. There's the cubic, there's the parabola, and we can see they intersect at 2 points. All right? They intersect here, and from here till here, the origin, the cubic is the top function. And then from here until here, the parabola is the top function. So we're going to split this into two integrals. The first integral we're going to do for this shape, finding the area of that region. And the second integral, we're going to do it for here. Now, we should first probably find our intersections. You can do this by hand, or you can do it on the calculator. I'll show you quickly, review how to do it on the calculator. We're going to do second trace, find the intersection. Now, there's only two functions on here, so when it asks first curve, you can just hit enter. When you can ask second curve, you can just hit enter. And now when it says guess, there's three possibilities. You need to guess which one you want. The first one we want, we're going to look at, try and get the one that looks like it's at -2. So enter a guess of -2 and see what it really is. It's -2. It's -2, -8. So this point right here is -2, -8. This point right there looks like the origin. If you think it's the origin, just plug in 0 and see if you get 0 out of both functions. In this case, we do. And then the last one, it looks like it intersects at 2. You can try plugging it in, see if we get the same number out. I'll do an intersection on the computer. Second trace, intersect. First curve, yes. Second curve is y2. My guess, I think it's at 2. And we'll see if I'm correct. I am. It's at 2, 0. All right. So there's my intersections. And now what I'm going to do, I'm going to do the green shape first. In the green shape, the cubic's on top. I stored the cubic in y1. So the green area will be from -2 to 0, because I'm stacking rectangles perpendicular to the x-axis. From -2 to 0, I did y1 on top, y2 on the bottom with respect to x. And I'm writing like this because I'm going to use the calculator to do it. And when I use the calculator to do it, as long as the functions that are in y are in terms of x, I can do it like this. Now for the blue function, it's pretty much the same thing, except we're going from 0 to 2. And now y2 is on top. All right, so there's my setup. I'll work the problem, get to a clear screen. And I'll do the integration. I'm going to do the green one first. So integrate from -2 Let's start over. from -2 to 0. And y1, I'll go to vars. It's a y variable, and it's a function. So I'm going to do y1 minus y2. Same key sequence to get to y2 with respect to x. And when I do that, I can see that the green area is 12. Then I will do the blue area. Same way, except I'll change my limits and the different functions on top. So math 9, now I go from 0 till 2, y2 minus y1 in this case with respect to x. And again, it's 12. Not always the case, just in this case. And the whole area from here to here, added up with from here to here, the whole area then would be 24. So the area between the two curves is the area of each individual section combined. Our next problem. Find the area of the regions bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. Now as you look at this one, these are oriented differently. These are in terms of y instead of in terms of x. So they're going to be graphed and they're going to look sideways. Right? So as you graph these, it's going to look like this. Our parabola, instead of being vertical, can be horizontal with a y-intercept or an x-intercept of 3. And our line is going to have, instead of this being an x-intercept, it's going to be a y. Or instead of being a y-intercept, it's going to be an x-intercept. So we're going to graph it. We're going to need to find our intercepts. I'm going to do that by hand on this one. I'll set those equal to each other. 3 minus y squared equals y plus 1. Let's get it equal to 0. So we'll have add y squared plus y, subtract 3, we'll get negative 2. That factors, we get y plus 2, y minus 1. So our intercepts are y equals negative 2 and y equals 1. You don't really need y-intercepts because we're going to go with respect to y. We're going to stack perpendicular to y. Right? We could go perpendicular to x, but look what happens right here when we go perpendicular to x. What's the top function? Well, the top function is the parabola. What's the bottom function? That's also the parabola. It gets to be kind of a sticky situation if you're going from one function back onto itself. So we're going to go flip it and go with respect to y. Now our limits will be our y values this time. So our area will be the y values. Our lower limit is negative 2. Our upper limit is 1. Now our top function, if we're looking with respect to y, the higher numbers are to the right. So our top function is going to be the function that's on the right. So we'll use the parabola. So we'll go 3 minus y squared minus our bottom function will be the one on the left, y plus 1. And this time it'll be with respect to y because we're oriented horizontally instead of vertically. Meaning our slices go horizontal. All right, so let's integrate this. I'm going to first distribute negative 2 to 1, 3 minus y squared minus y minus 1 with respect to y. I'm going to combine like terms, negative 2 to 1, 2 minus y squared minus y dy. All right, now we can integrate. We'll have 2y minus 1/3 y cubed minus 1/2 y squared from negative 2 to 1. All right, we'll plug in 1. We get 2 minus 1/3 minus 1/2. We'll plug in negative 1/2. We'll get negative 4 minus negative 2 cubed is negative 8. So minus a negative 8/3 minus, okay, negative 2 squared is 4. 4 over 2 is 2. All right. Simplify that. 2 minus 1/3 minus 1/2 minus -4 plus 8/3 minus 2. So that works out to be about 4.5, or as a fraction, 9/2. If you're not sure how to convert to a fraction, hit math, and it's the first choice. So the area between those two curves oriented with respect to y is 9/2. So in conclusion, how do you find the area between two curves? Well, you're going to integrate each area individually and subtract them. Or just do it all at once. From a to b, the top function in terms of x minus the bottom function in terms of x with respect to x. Or if you orient it just slightly differently, you're going vertically instead of horizontally, we'll go the right function in terms of y minus the left function in terms of y with respect to y.